So this paper, which we are going to talk today, LLaVA-3D, a simple yet effective pathway to empowering LMM with 3D awareness. So let us unpack. These days, people put quite a bit into the title, and sometimes I feel that unpacking the title is half the story because the titles are quite carefully written. So what are LMMs? Large multimodal models. When when people use the word LMM, and these days you start seeing a variation. LLM is large language model. LMM is large multimodal models. LAM are large action, LAM are large action models as an agentic framework and open function calling, and so on and so forth. So these vocabulary is growing these days. LLM has been there somewhat interchangeably, and I wouldn't say too far off. The so-called vision language understanding as is an adjacent topic or the same topic. Frankly, you do vision language understanding using LMM, large multimodal languages. Now, 3D awareness is self-explanatory. What it means is you're trying to build a model that is capable of understanding the 3D-ness of the real world. It doesn't mean necessarily that you will give it 3D data. It just means that given a 2D image, it will nevertheless be aware that 2D picture represents an inherently 3D world. And the question is, how do you empower an LLM with that 3D awareness? That is the question. And what they are suggesting is they have a model, LLaVA-3D, a simple yet effective pathway to empowering LMM with 3D awareness. Now, this LLaVA itself, there's a bit of history to it. This has been one of the most successful LMM series. The LLaVA went from 1.0 all the way to 1.5, and then there are LLaVA Meds, LLaVA this. There are so many variants that have come to LLaVA because it was found out to be such a wonderful idea. It's one of the dominant LMMs, large multimodal models out there. Very effective and quite capable. So obviously the right way to do that is to first build up a little bit of a history, a little bit of a background in LLaVA itself, which we will do shortly. Right? So I'll just put a question mark. What is this? Because this paper is a very simple extension of LLaVA, but nevertheless a very powerful extension. What it says is that if you want to create 3D awareness and imbue LMMs with the ability to interpret and understand 3D, you can do it using a simple yet effective methods. Right? So you don't have to go about creating 3D, realizations of the world, image or data points of the world, and do it using that. You can do it much more simply. So that is what the paper is about. Now, before we do this, let me just give a very quick background on LLaVA. LLaVA is a paper that in our paper reading series we have covered in the past. So the best way to explain LLaVA is to see its consequence or what it achieves. And then we'll go back and see what LLaVA-3D achieves. So sorry for scrolling so fast. So let's see how well it does. First of all, observe how well it does here in this picture. Comparing LLaVA GPT-4 and how well it does against the competitors. As you know, GPT-4, at the time of the writing of this paper, which was last year, was the state-of-the-art model. You put this image that you see here this image, and you ask, can you explain this meme in detail? Right. So so let's see what GPT-4 says. GPT-4 says, this meme is a joke that combines two unrelated things, picture of the Earth from space and chicken nuggets. The text of the meme suggests that the image below is a beautiful picture of the Earth from space. However, the image is actually of chicken nuggets arranged to vaguely resemble blah, blah, blah. Blip 2, by the way, was a state-of-the-art large multimodal model at the time of the writing of this original paper. Blip 2 doesn't do as well. It says, sometimes I just look at pictures of the Earth from space and marvel how beautiful it is. That's the way it explained or answered that question. Flamingo, Open Flamingo, as you know, Flamingo is a very influential architecture in this space. It also doesn't do as well. It's a picture of a chicken nugget on the International Space Station, which is essentially hallucinatory. So with this as a backdrop, let's see what LLaVA has to say. What LLaVA says, the meme in the image is a creative and humorous take on food with a focus on chicken nuggets as the center of the universe. The meme begins with the phrase, sometimes I just look at pictures of the Earth from space and I marvel at how beautiful it is, which, by the way, was there in this here, right? Which is what Blip just managed to pick up on. The main image features a tray of cooked chicken nuggets with the chicken pieces positioned to resemble the continents and the islands on a world map. The meme playfully suggests that the chicken nuggets represent the Earth and the various locations, etc. The punchline of the meme appears in small text at the bottom, reading, I mean, it's not the real Earth, but how beautiful it is. It all is. This light-hearted and entertaining meme combines food and humor using the image of chicken to create it. And as you can imagine, if you were to look at vision language understanding, ability of a machine to understand a picture, because a picture is a vision language, it's a visual language of expression, you would agree that LLaVA's understanding of the picture is superior to the alternatives, isn't it? And how it does it is, we'll talk a little bit about that. And look at this, what it does. You can give it, a user can give it a picture like this, turn this mockup into an interactive website using HTML, JavaScript, replace the joke with a real joke. That is tough. I mean, if you think in terms of multimodal or vision language understanding, it is saying that I'm giving you a hand drawing, a mockup of a scribble of a page, web page. You have to draw it out. And look at this. It manages to write a perfectly good thing. Here it is. Here's a little web thing it produced. Welcome to my joke website. Push the button to reveal the punchline. You push that button, and then it reveals the punchline. The punchline is, why was the math book sad? Because it had too many problems. Right? Now, I don't know how you guys look at it. Obviously, this was last year. Trust me, last year it was very, very impressive, especially for an open source model to do it. So the question is, how did it do that? What it did was remarkably simple. Actually, is the sheer simplicity, and I'll come to that. So there are many, many examples. You give it a picture like this, and you ask, what is the ending of this movie? Do you realize that you're not asking something, an answer that is in the picture? You're asking it to understand the picture and then say something. And this is the fun one. What do you think? Do you know who drew this picture? Right? This one. And then it goes on to say, the painting depicts a dog in a humorous situation where it appears to be wearing a woman's dress and standing in front of a landscape, etc. So it figures it out that it's a work of Mona Lisa, the spin on Mona Lisa, and so on and so forth. So how does it do it? In very short form, the way it did it is actually dead simple. See, to train a large language model, first, of course, what do you need to do? So how do we train a large language model? I'm sorry, why am I not able to write with it? Oh, something very weird is going on. Okay. And whatever I'm writing is disappearing. So let's try a look. Oh, it is not disappearing. It just disappeared for a while. So see, there is a concept called instruct. So this paper's actual title was that introduced LLaVA was instruction tuning, visual instruction tuning. Now, instruction tuning is important because if you remember, instruction tuning led to one of the first earliest alignment of a large language model, of a transformer to answer questions better, right? So you need instruction tuning. Instruction tuning, how do you do that? Typical instruction tuning is answer. So suppose you can give an instruction, answer with yes or no, right? And then some question may be given. What have you done? You have prepared your question with some instructions so that the machine is allowed to produce only yes or no as answer. And you can tune it. You can train the machine to behave or follow the instructions, right? So for that, what do you need? You need a lot of instruction tuning data. Always, these machines need to be given the xi and yi, namely the input and the output, and then you sort of train the machine using a causal loss function, and then you can essentially train it. But the whole question is, and the remarkable idea there was, how about visual? Given an image, how do you instruction tune? To instruction tune, you need a vast data set like this. Textual data sets for instruction tuning do exist. Visual instruction tuning data didn't exist, right? So what you could do, or what this paper does, is it says, okay, let's see what parts of the puzzle we know how to solve. We know there is a LLM we can borrow. We can take an image and we can break the image up into patches. Remember, this is the VIT paper, 16 by 16 patches, pixel patches. So let's say that this is a patch. This patch, I can create it. So this XA, this particular vector, let me just say visual vector, I can take X visual. I can also take, suppose I happen to know something about some input, some text, which I'll write it as a question. Right? I can jointly project it into, so use some projection matrix, projection network, projection feed-forward network, to align it to a large language model. Now, how do I do this? For example, CLIP does a very good job. Remember, what does CLIP do? CLIP produces a embedding of a picture. Do we remember that, guys? A CLIP is a contrastive loss image pre-training. It's just a model that, given an image, will create a semantic vector out of it. Very much used for search, multimodal search, and so forth. So it would create the vector. Now, your text, of course, another transformer, a simple text transformer will give you XQ, right? A text encoding. And what you can do is you can say these two jointly embedded is the input, is the XI of the model that I was looking for, and yi is the answer to the question. Answer to the question about this image, right? Now, if only such a data set existed, right? You have an image, you have a nice input question, and you had a good, nice answer that you expect in response. Such a data set didn't exist. But this is the architecture that, this is your basic, assuming that such a data set existed, this is your basic training architecture of the LLaVA. the LLaVA architecture, a very successful large multimodal language. So how do you create such a data set? That's the big question. So what they did is something quite interesting. They said, okay, we are going to take an open source model. I believe they took, in those days, Vicuna was doing very well. They took a open source model called Vicuna, and now today you will use whatever Llama 3.2 or whatever it is. But in those days, that's what they did. And they took an image like this. So let's observe this image. This is people packing something into an SUV. So here is the caption to the image. A group of people standing outside of a black vehicle with large luggage, with various luggage surrounding a vehicle, etc., etc. So it's a SUV, blah, blah, blah. So you take an image that is known to be captioned, right? That image, the captioned image, for example, you could have gotten from the clip, the data set used to train clip, or Blip 2, for example, is very efficient at captioning images. You take an existing large multimodal model, and you have it generate a nice, good caption for the image. Then you can also do bounding boxes, location of the images, and you would come up with this, exactly where each of the things are. You know, you see those rectangles, colored rectangles. So that's segmentation. You do that. And then what you do, you go to a model like GPT-4, and you say that if I did not give you the picture, but just gave you these two, given this caption, the context, and given the bounding boxes, could you generate question and answer? So this is what the machine can generate. Can you generate good question answer pairs from the image? Does that make sense? Right? So step one is go to a much larger model. And remember, to the model, that model is not like GPT-4, for example, is not a multimodal model. It is just a text model. What are the texts you are giving? These two texts, not the picture. And you ask it to create a set of question answer things like this: question, its answer, complex reasoning, etc. You ask it generate interesting questions, not hardwired questions. Because if you create hardwired questions, all you will say is, what does this image describe? Which will be silly. Right? It won't be specific. So you make a much larger model, think and create interesting question answer pairs. Now you do it for a vast repository of image. And now what do you end up with? You ended up with the thing that you were looking for, namely, if you go back to our architecture that we drew, see, what were we searching for? We were searching for this, isn't it? So given an image, if we first pass it through a machine that generates QA, question answer pairs out of it, then we can play this game. We can give the image and the question, pass it through the network, feed it to the LLM, and fine tune a small LLM, an open source LLM, to produce XA, right? To emit out the answer to that question. And that is the most remarkable thing that you could do. And the mathematics of that is actually pretty straightforward. If you look at it, you take a vision image vector, and you take a text vector, the question vector that you just created. What will an image encoder like CLIP do? It will produce a hidden state. This will also produce a hidden state. And you produce that hidden state. Like, for example, image encoder, you may say, wait a minute, you may use Vicuna, but the input vector it expects is maybe 300 dimension. And the vector that a CLIP produced is maybe 200. I mean, I'm just randomly throwing numbers. Is a different dimension. So then what do you have to do? You have to transform it into the right input dimension. All it takes is a matrix, a projection matrix. You take a projection matrix, and then encoder will encode, and then this will encode. Text encoders are, of course, the standard. Use anything in the bird family, it will give you that. And then after that, now that you have aligned it, you pass it through a language model. Here they took Vicuna and they sort of fine-tuned it. And in subsequent work, they replaced it with Llama and so on and so forth. So then the response that you expect is this. This is all that there is to it. Now, look at the sheer utter simplicity of it. If you were to look at it a little bit more mathematically, you're basically saying you want to maximize the probability of XA in your model by training the weights and biases of your LLM in such a way that you maximize the probability of XA given the image and given the instruction, maybe the question, right, with the augmented with some instructions. And that's all it is. So that was the big idea. And when you did that, the results were surprisingly good. Like, for example, here's a good case. What is unusual about this image? Right. And it goes on to say the unusual aspect of this image is a man ironing clothes on the back of a minivan or van. This is not a typical place to perform this activity, right? As one would usually iron clothes in a more stationary and safe location, and so forth. So it's remarkably good in it, right? So that was the backdrop. So what the authors of this paper that just came out 1 week ago, not even a week ago, yeah, almost going to be a week. Today is 2nd, and this came out on 26th. What they are saying is that, see, people have been trying 3D multimodal models, 3D awareness in multimodal models, but they are struggling with it. So, for example, if you look at this, this image is worth looking into. One second. Look at this image. Look at this radar graph. Each of these is a benchmark. And each of these colored lines that you see is some multimodal model, right? And you do notice that none of them seem to be like, they do well on one thing, but not the other. For example, if you look at Chat 3D V2, where is that? It is this green line. I'll draw it out. This one. Oh, sorry, that's way too fat. Do you see this, guys? I'll just emphasize it here. So it means it does very well on SQA 3D, does reasonably well on Scan QA, not so well in Scan QA benchmark. Some tasks it does well, some tasks it does horribly, right? On the other hand, if you look at the approach that this paper is proposing, this paper is proposing an approach which is given by LLaVA-3D. And what is the performance of this model on all these benchmarks? Do you notice that it seems to be achieving the state-of-the-art performance on every benchmark, isn't it? So obviously, when I suppose when a paper starts out with results, and which is becoming increasingly common these days, figure one often brings out the compelling value of an approach. And they seem to have made their point with one result in itself. It says, in one point, look at this, we beat everything. Now the whole question is, how did they do that? What is the approach? So the approach that they take, once you understand how LLaVA works, is very simple. And I'll keep this short because we're running out of time. We have run out of time, but I'll take another 15 minutes. What they are saying is that, see, LLaVA is really an amazing model for 2D. So what if we did this? We took LLaVA and we didn't screw it up, but we fine-tuned LLaVA with 3D awareness, just imbued it and augmented its ability with 3D awareness. So if we could do that, we would have a winner, isn't it? So then the whole question is, well, that is easier thought than done. How would you do that? It turns out that they do it in a surprisingly easy way. There's no magic. It's exactly the same approach. So what do they do? First of all, given a situation, you can have multiple views of it. Suppose you have multi-view picture. You take a room, you have 5 different shots. What will happen? A single shot may not be able to convey the 3D awareness, but the moment you take more than one picture, inherently, if one thing is present in 2 images, you're looking at it from 2 different perspectives, right? And so that becomes agent for inducing 3D awareness into that, right? In a way, two pictures are conveying together a 3D information about a scene. And so what you do, and what they do is something very simple. They take, and there's a bit of technical details, but they take multiple views. Now, typically, remember that in 2D, you would take one patch, right? You would break it up into patches. But now there's more, because there is not just one image, there is another image, right? Actually, even for a 3D patch, there are three channels. There is the color channel, there is the height, and there is the width of a given pixel, isn't it? Any pixel belongs to, basically, therefore, vector space, X belongs to color, height, and width, color cross height cross width, right? A three-dimensional world. But here, there is a fourth dimension, which is which of these views do you belong to, right? So you need to bring in the view also, view cross this. Are we together? So now we are looking at, okay, which view, which color channel, red, blue, green, and what is the height and width location of that pixel. As simple as that. And so what happens is that when you create the 2D patches, the way you would do it in CLIP, you can do that. But now, and as you know, in the encoder, you need to create positional awareness, right? Where exactly is this patch? Because if you convert a little patch into a vector, the question remains, it's just like with words. You can take the sentence, the cow jumped over the moon, and you can encode the word moon. You can do a word embedding of it. Nevertheless, you need to still specify where was the moon, right? So at the end of the sentence, beginning of the sentence, where was it? So you need to do position embedding. So the same thing they do here. There's a set of techniques to create a positional embedding awareness, which you embed, of course, into the patches. But what will you get? You will then get this information here. Now, what happens is that this becomes computationally now a little bit more intense than you would want, because it's a lot of little patches, right, that you have created. So you need to do some sort of pooling or some sort of a data reduction. The two pooling techniques that they talk about, one is voxelization. Voxelization is just a 3D generalization of what you would do in 2D. So for example, how do you do min pool or average pooling? You would take, let's say that you would take a pooling filter, and you would take the value A, B, C, D. You make it sit upon the image or the feature map, and you take the value. So min pooling would take min, average, or max, which literally means pick the smallest, the biggest, or the average of the values. But you replace 4 of them with 1 point, right? So that is a significant data reduction, isn't it? So you sort of compress it a little bit. So now can I generalize this in 3D? Right? It's a voxel. Voxel, by the way, is a very similar, very obvious generalization of a pixel. Right? 3D locationally, you generalize it. So you can do voxel pooling, which is a very simple generalization of your standard pooling, or you could do FPS pooling, a farthest point sampling pooling. What in the world is that? So I'll give you a very simple intuition on what it is. Suppose you have a lot of points. The word people use is point cloud. Suppose you have a point cloud. What you do is pick a random point, right? So let's say that I pick this point, right? Find the point farthest from it. Suppose I want to do FPS pooling, and I want to have FPS pooling using 5 points. So what I would do is I would take this and find the farthest point. Here, looking at it, one would argue that perhaps this looks like the farthest point, isn't it? Top right. Do that. Now ask this question, which point is farthest from both of them? Right? if you were to look at that, you would probably hazard a guess. If I have to hazard a guess, I would say this is farthest from that. And then I would say, okay, pick a point that is farthest from these 3 points, right? Whose distance between this is more than that of some all other points. I don't know which one you would pick. Maybe you would pick this, right? And you would pick this, something like that. And you would say, okay, if k is equal to 5, then you replace it with just these data with the point cloud, now reduce it to just these 5 points, right? So that is called FPS pooling, farthest point sampling pooling. People use this. This paper goes on to say that that doesn't actually work as well as voxel pooling. But nevertheless, you can do the pooling, sample it out. The rest of the paper is actually very straightforward. It just says, use the language, use the same technique that you used with LLaVA for this situation. Because now you can take this pooled data, you can do exactly that, project it using a clip-like technique. But one important thing to do is 3D position embedding. You must inject the 3D position of that patch, right? Generalize it to 3D. And then the instruction tooling is your XA, remember? And the same thing you do, so long as that those group of images are captioned, you can pass it through the same technique, through a bigger model, get that, and then you can train this model, and so on and so forth. And there's more technical detail to it, but I notice that we do seem to have run out of time. So that is the core idea. And if you do that, train this, you do end up with a very successful model, as we saw. Let's see, does it actually work? It's quite remarkable that it works, actually. Let's look at this. I hope this image is visible. So you give it this group of pictures. And usually in the demo, they're saying, let the user click on any object. So here the user seems to have clicked on this object. What is that object? If you look at this carefully, what is that object? You'll have to stare quite a bit, but it's basically a black chair, right? And then you say, given the 3D scene, describe and localize this object. So it's a very simple task, describe it and see what it says. And it says localize it and see what it produces. It says the chair is a black chair with a back and seat made of polyurethane or leather and has a smooth texture. So because it saw this chair at 2 places. It saw the chair here. It saw the chair here. It didn't see the chair in these 2. It saw maybe the little bit of the chair here. It didn't see it here. And I don't know if this is it. I don't think so. This is it. So this is it. And so it is told, localize this. And when it tries to localize it, would you say that it has created the right location for this chair with respect to the furniture? Right? Look at this. It has contextualized this chair here with respect to the bed, with respect to the table, and so forth. And it says it is used in an office as a desk chair and has a swivel base and is directly facing the brown leather desk. And it says it has figured it out that there is a brown, sorry, not leather desk, facing the brown desk, I suppose. Wood is brown. So it did it. This is a little bit more interesting, 3D question answering. You're asked, what is the only object you can see in the other room? So implicit is that there are 2 rooms here. So obviously, if you look at the first picture, there seems to be the stuff. Second picture. In the third picture, there seems to be another room, a door visible. And you are being asked, what's there in the other room? Right? So you're basically asking, what is here? Right? And it has to figure out that this picture refers to the object in the other room, right? And it says a blue bed. And the related object is located at blah. What is the region role of this object? And it says, well, the shelf is placed above the desk, making it convenient to access books and study material. Well, I suppose that's one interpretation of it. So there are more and more examples. But suffice is to say that this model does, as far as I can make out, seem to work quite well. Okay? Some of these are actually a little bit hard. Nevertheless, it manages to get it right. One that I found quite remarkable was this. You click on this, right? The related object is located at blah. Looking at the front of the object, select the cabinet that is to the left of it. It's a little hard, actually. If you look at this picture, I don't know how many of us could immediately figure out what is to the left of it. You're asking, what is here? Isn't it? What is to the left of this clicked image? And it is able to do a very good job of that because it looks through all the images and figures out that the cabinet is full of ovens. This guy is to the left of it. Right? And it takes some time to realize that that happens to be true. So, all right, guys, I'll end the paper reading now. Suffice is to say that this seems to be a promising result in large multimodal models. And any questions, guys, before I end it? I don't know, did you guys, I hope you guys had fun with this paper. Multimodal is the new frontier these days. We are heavily, especially 3D and multimodal, both for discriminative and for generative tasks. It seems to be the absolutely hot topic today or these days. All right, I'm going to stop the recording and open us up for more question and answers as needed.